Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in this enlightening session of MSc Final Physics. I am dealing with fifth paper, Condensed Matter Physics. In my previous lectures, we have discussed about superconductivity. Now, in today's lecture, I am going to start magnetic materials. So initially we will start with classification of these magnetic materials. What is the cause of magnetism? In any material, magnetization arises because of orbital and spin motion of electrons, as well as there is also interaction of electrons with one another. So we can classify different type of materials on the basis of their orbital and spin motion, and this is the base of classification of magnetic materials. The behavior of these all materials is different when they are placed in magnetic field. In nature, we can see that all materials are magnetic in nature. We can classify these magnetic materials into five major groups: diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, and antiferromagnetism. Now we will discuss these five kinds of magnetization. First is the diamagnetic material. Diamagnetism is very weak magnetization, and it arises because of non-cooperative behavior of orbiting electrons when they are placed in external magnetic field. When these materials are placed in a magnetic field, negative magnetization is generated, and these are composed of atoms in such a way that there is no net magnetic moment. That means the orbital shells, they are filled and there are no unpaired electrons. The plot of M versus H shows that susceptibility is negative. Since chi is equal to M by H, we can see clearly that susceptibility of diamagnetic material is negative, and when there is no field, magnetization is also zero. The another important parameter of diamagnetic material is that their susceptibility chi is a temperature independent property. This shows the variation of chi with T, that it is independent of temperature. Examples of diamagnetic material are quartz, calcite, and water. These diamagnetic materials, they move from stronger to a weaker field. And when we take a diamagnetic rod and we suspend it in a magnetic field, this freely suspended diamagnetic rod, it will turn at right angle to the applied field. That means they are magnetized in a direction opposite to the applied field. Because of this property, they will have a very small value of intensity of magnetization. Now, moving over to the another type of magnetization. The another type of magnetization is paramagnetism. In this class of materials, there are atoms or ions which have a magnetic moment because of unpaired electrons in partially filled orbitals. Now, in the presence of magnetic field, this partially filled orbitals will generate magnetization, which will be positive, and hence they will have positive susceptibility. This shows the graph of M with H. This graph shows that susceptibility, when obtained from the slope, it is positive. As chi is equal to M by H, we can easily obtain from the slope of M versus H curve. And variation of susceptibility with temperature is shown in this graph. The variation of susceptibility with T follow the Curie law. Chi is inversely proportional to 1 by T. This is Curie law. Susceptibility along with positive value, it has a very small value. And magnetic lines of forces inside the material placed in magnetic field are more than outside it. That means, let us suppose we have a paramagnetic material and we place it in a magnetic field. Then inside the material, the field lines will be more than outside. Examples of paramagnetic material are non-trollite, biotite, pyrite. Now I am moving over to the third important form of magnetic material, that is ferromagnetism. Ferromagnetic material, we are all familiar with iron. Iron is a ferromagnetic material. These ferromagnetic material are highly magnetized in a magnetic field. We know that if we have an iron nail or iron fillings and we place it in a magnetic field, then it will be attracted towards it. Their behavior is different from paramagnetic material. Unlike paramagnetic material, the atomic moment in these material exhibit very strong interaction, and this interaction is produced by electronic exchange force. This exchange force is a quantum mechanical phenomena and it arises because of orientation of spin of two electrons. In these ferromagnetic materials, we have parallel alignment of moment. This shows the parallel alignment of movement of different electrons. This results in a net magnetization even in the absence of any field. Ferromagnetic materials are highly attracted by magnet. If we suspend this ferromagnetic rod in magnetic field, it will turn fast to set along the magnetic direction. The well-known example is iron. The other examples are nickel, cobalt. They have a magnetic susceptibility which is positive and it is very high, and the magnetic susceptibility varies with the applied field. The permeability of these materials is also very high. Paramagnetic and ferromagnetic materials are different. We can compare them. Paramagnetic materials have chi of the range of 50 when measured in unit of 10 raised to power minus 8 meter cube per kg, whereas ferromagnetic materials have a susceptibility of 1000 to 1 lakh. Now, the fourth class of magnetic material is ferrimagnetism. Ferrimagnetism arises in oxides, which are ionic compounds, and these ferromagnetism structure can be system composed of two sublattices. These two sublattices, they are supposed to be separated by oxygen layer. Oxygen is an anion and there is an indirect interaction, or we can say that there is a super exchange interaction between these two sublattices. These sublattices have anti-parallel alignment of spin. I have taken my sublattice to be AB, so there will be strongest super exchange interaction which results in an anti-parallel alignment of spin between the A and B sublattice. In ferrimagnet, the magnetic moment of A and B are not equal and result in a net magnetic moment. So, ferromagnetism is similar to ferromagnetism. Apart from the presence of magnetization, ferrimagnetic material show the properties which are similar to that of ferromagnetic materials. Properties are Curie temperature, hysteresis, remanence and spontaneous magnetization. The difference between ferro and ferri is that they have different magnetic order. Example is magnetite. Initially, magnetite was considered to be ferromagnetic, but Neil discovered that magnetite is not a ferromagnetic material, it is a new class of material which he named as ferrimagnetic material. The another form of magnetic materials is antiferromagnetism. Here similarly we have two sublattices A and B. The magnetic moment of these two sublattices are equal and opposite, so that net magnetic moment is 0. This class of magnetic ordering is called antiferromagnetism. Now, to study the susceptibility, there is a temperature variation of susceptibility. At temperature, Neil temperature termed as susceptibility changes. Behavior of susceptibility above the critical temperature Tn follow the Curie-Weiss law for paramagnetism with a negative intercept indicating negative exchange interaction, because there in this case the spins are anti-parallel to each other. So in nature we have materials which are magnetic in nature, and they can be classified into 5 broad categories depending on their behavior to the external magnetic field as well as their internal behavior, which is the orbital and spin motion of electrons. Thank you students for watching.